invitation. So, yeah, I'm going to talk about the following result. It's about testing equivalence of polynomials under shifts, and it's a joint work with Zeev Dvir and Rafael Oliveira, both from Princeton University. Okay, so what I'll do is I'll start by presenting the problem. I will give some background, I will speak about relevant results, and then I will show the proof. So what is the problem? So in the problem we have to solve the following question. So it will be, in some sense, it will resemble the PAT problem that we already heard some talks about, but it will be of slightly different nature. So we'll be given two polynomials, f of x and g of x. And we'll have to explain what we mean by given. Okay, it will be different in different scenarios. It will be a different meaning, but you have to decide whether there exists some shift b such that after this shift, f of x is identically equal to g plus the shift b. So both of these things will be over fn in x1 up to xn. Okay. F of x1 up to xn. Okay, so and b, so b of course would be a shift in f to the n. Right. So basically what this means that you replace x1 by x1 plus b1, x2 by x2 plus b2, etc. And you want after this change to have the same polynomial. So this is a problem that we call the shift equivalence testing. Right, you're given f and g, and now given can be either I give you arithmetic circuits, I give you arithmetic formulas, I give you sparse polynomials, either white box where you can see the computation, or black box where you only have query access. Okay. So first of all, one quick observation is that polynomial identity testing is a special case of shift equivalence testing. Why? Because think about G as being the zero polynomial. Then any shift of the zero polynomial is still the zero polynomial. So basically f is shift equivalent to zero polynomial if and only if f is zero. So this is a special case of PIT. Now so PIT is a special case of, let's call it shift equivalence testing. So SET. I'm much too violent for these delicate chokes. Typical Israel. So PIT reduces to SET. Okay. Now. So clearly SET is more difficult, right? Because PIT reduces to it. And one can ask, what is the complexity of SET? Is it as difficult as PIT? It's more difficult. Now, I think the first thing one notices is that SET has the following structure in some sense. Let's say that it was a Boolean question. Okay, so what is written here is whether, what you have to solve is whether there exists some b such that for all x, and then we have something, right? F of x equals g of x plus b. Right? This can be viewed as the question that we are asking. And if you think about a Boolean world, this is a sigma 2 problem, right? So it's unlikely to have efficient algorithms if we take this to the Boolean case, right? Whereas PIT does have efficient algorithms, at least efficient randomized algorithm, right? The Schwarz-Zippel, the Miller-Lipton lemma, etc. So what we prove in this work is that essentially, and I will make this more formal soon, PAT is equivalent to SET. In the following sense that
it is not sigma 2, it is just written in the form of sigma 2.
Yes. No. Just say that intuitively, I mean, when you look at this question, it might look scary because this is the form, but I agree, right? Because PAT is this question, right? And it's not Cohen PR, right? So I agree, but it just seems one more level of complication compared to PAT because you have another quantifier. So that's what I meant, right? PAT, you can think about it as asking this question, we just add another quantifier. And so we show this. So one direction is clear, right? To solve PAT, it's enough to solve SET, right? But what we show basically is that you can solve SET by asking several PAT questions. In particular, this gives a randomized algorithm for SET, right? And if you look at the question, it's not clear why should one have a randomized algorithm? Because we are looking for, there might be a unique B that gives this shift. So how could randomness help? But apparently you can solve the problem and find, I mean, when I said you can, so this is, I stated the problem is a decision problem. You can also ask for the search problem. Decide if there is such a B, and if there is such a B, return that B. So this is actually what we do. We ask several PAT questions. At the end, we will know whether such a B exists, and we'll give that B. Now, PAT, we don't have efficient deterministic algorithms, right? So this gives a randomized algorithm for SET. However, we can also show in certain scenarios that deterministic PAT algorithms translate to deterministic SET algorithms. Okay? So what I'll do is I'll now say the theorem more formally, and I'll draw some conclusions from it. Yeah, Michael.
So the B would always actually be in the base field, right? Because this is like solving an exponentially large linear system.
Yes. So it's more than a linear system, in fact, right? It's
not homogeneous.
I mean, if you just expand G, you'll have high degree monomials in B as well. But
so then why? Okay, so if it is true, the B would always be in the base field.
Yes.
Is that clear?
Is that clear? I think, no, it's not clear when you look at it, but it will be clear. I mean, just the proof will, well, yes.
What's the question? If there is a B?
No, the question is whether B has to be in the base field.
If there is one.
Yes, if there is one, but it has to be in the, yes, it will be in the base field. I think so. We'll see. I mean, if I'm wrong, we'll catch it. I hope you'll catch me. Okay, so let me state the theorem more formally, and then I'll speak about related work, and then I'll give you many chances to catch me because I'm going to cheat. I mean, I don't think I'll say anything accurate today. Okay. So this, okay, so let's see. Let's keep the problem on the board. Okay, so here's a theorem. So I'll try to specify what given means. So given F will come from a certain circuit class, and G will come from some other circuit class. And I will write the conditions that I want the circuit class to satisfy, the circuit classes to satisfy formally. Okay, so it's not here. Okay, it's not here. Okay, so by M1 and M2 to circuit classes. Okay, so let's assume the following. Let's assume that, okay, perhaps I have to explain a few things. So I will say that M1 is, what I require M1 is to be closed, and I will explain what it means under. So A, like homogeneous components. B, I think, yeah, first order partial derivatives or directional. So what do I mean by this? So M is some class of circuits. It computes some polynomials. Now, a homogeneous component of a polynomial, we already saw what it means. Right? It means all the monomials of a certain degree. So what I want the class to satisfy is that if it computes a certain polynomial f, then each of the homogeneous components of f can also be computed within the class. Now, if you think about general arithmetic circuits, then certainly it's satisfied, because we can, I think we've already seen it, and if not, I can explain again, how to get the homogeneous component of a polynomial. Just a larger circuit, but it's still an arithmetic circuit. The problem comes when you think about very, very restricted circuit classes, and then some of them are not closed. For example, if you think about, say, we've seen depth-first circuits. So if you think about depth-first circuits with bounded top fanning, then it is not clear that taking a homogeneous component will result in a bounded top fanning. It may require a larger top fanning. Okay, so I'm just writing everything that I need from the circuit class, and if you just care about the randomized result, then you can think that N1 is just the class of all arithmetic circuits, or all polynomial size arithmetic circuits, and that will be okay. But if you also want to get like to really very restricted classes, then you want to take into consideration these requirements. Yes?
Some amount of time.
So I didn't explain what B means, but yeah, so B means first order directional derivative. Now what is a directional derivative? It's an object of the form summation of alpha I df to dxi. Okay? So this is an object I call directional derivative. So let's say, so I want to be not, okay, so let's take an example. For example, if each, let's think for example about a polynomial with, I don't know, k monomials, okay? So each derivative will also have k monomials, because the derivative of a monomial is a monomial. However, such a thing can have n times k monomials, right? So it has more monomials, right? So if you think about sparse polynomials, the sparsity can grow by a factor of n. So let's say that we have some like the definition of P, right? That if I'm looking at circuits of size polynomial from a given class, then I want this to be a polynomial size circuit from that class. For example, if you want to have an example of M1 at mind, so either the class of all arithmetic circuits or the class of polynomials with only polynomially many monomials. So both these classes satisfy A and B. Yes?
So we want to say is that you have some circuit with some structural restriction with maybe some measure, and the measure can grow quantitatively?
Yes, let's say. Oh, yeah, just like the definition of P in some sense, yes. Yeah, I mean, yeah, I didn't know whether I should state the thing formally or not. And, okay. Well, if you don't restrict the class too much, then it will satisfy B.
Okay, if
but,
the definition is via size, it was actually.
Sorry, if
the definition is via the size, I mean, if you're restricting via the size.
So the size can grow, so that's a problem. I mean, the size can grow by a factor of n. But for example, a class that does not satisfy this, doesn't satisfy this is, say, depth-free circuit or depth-first circuit with bounded top fanning, because the fanning grows by a factor of n. And while we have deterministic PIT algorithms when the top fanning is small, we don't have it when the top fanning is large. So this class, I mean, I will not consider it to be M1. Okay, but again, if you don't have all the special circuit classes in your head, just think that about M1 as the class of all arithmetic circuits, and that's okay. Okay, so I don't have enough room to complete it here. So, okay, let me. So this is M1, and what I want now is I want M2 to be closed under shifts. Namely that if you compute a polynomial, some polynomial f of x in the class, then also f of x plus b is in the class. Now again, this seems like a trivial requirement. In particular, for example, depth-free circuits satisfy this. Because you shift the variables, it remains a depth-free circuit. On the other hand, if you think about sparse polynomials, take even one monomial. What happens to it when you shift it? You get 2 to the n many. So again, so if you go to very restricted classes, some of them do not satisfy this. So, I mean, you can think about one example here is like, again, general poly-size arithmetic circuits satisfy both. Okay, but that's of course the most general class. But if you want to have a special restricted class in mind, then here you can think about having sparse polynomials. So they satisfy A and B. The sparsity grows by polynomial factor, but it remains polynomially sparse. And here you can think about, say, just an example, depth-free circuits with bounded top fanning. So I think that Nitin, or Mike, I think Nitin introduced this notation, sigma pi sigma k. Okay, so the top fanning is bounded by k. Okay, so this class of all arithmetic circuits is certainly good enough, and 2 special classes, if you want to have in mind, are also want to have. Okay, so this is what I require of M1 and M2. And in addition, what I need, perhaps it's just like this. And I also want a polynomial identity testing algorithm for polynomials of the form f minus g, where f is in M1 and g is in M2. Okay, so I would want to be able to compare polynomials from f into g. So if I have 2 such circuit classes and a PIT for them, then basically we can solve we can solve SCT. And I'm not writing what I'm doing, just, depending on the running time of this PIT. So the running time for the SCT algorithm will be basically polynomial. It will require polynomially many calls to the PIT algorithm. So reduce SCT to PIT. Sorry, you can solve SCT for f in M1 and g in M2. Namely, you will give me f from M1 and g from M2 and ask me whether there exists such a B, and using polynomial many calls to the PIT, I will be able to solve the problem. Now, now you can ask about the white box model and the black box model. So it all depends on the PIT algorithm. If the PIT is white box, then I will require that f and g will be given to me as white in the white box model. If the PIT is black box, it will be okay that f and g will be black box. Now, if you think about this theorem, so think about the case of general arithmetic circuits. So certainly M1 and M2 can be general circuits, so f and g can be general arithmetic circuits. And we have PIT, a randomized algorithm. So this gives a randomized algorithm for the case that f and g come from just any 2 arithmetic circuits. However, if you think about more restricted classes, like sparse polynomials and depth-free circuits, you can also solve the problem for that model. And this generalizes the result of Chandan, Ramprasad, and Nitin that showed how to do PIT for depth-free and sparse polynomials. Now you can do more than PIT. You can also answer whether there exists a shift under which the 2 are equivalent. Okay, so you can do things for classes for which, or you can compare 2 sparse polynomials and ask whether one is a shift of another, for example. Okay, now it's more delicate, but okay, never mind. So this is the result that I'm going to talk about. Okay, so let me talk about related work. So we are not the first to ask this question. So there was a series of work by Grigoriev, Karpinski, Lakshman, and Saunders, I think back in the 80s and 90s, that asked really asked the same question, but they asked it in a slightly different setting. In that setting, they were interested to know whether is f a shift of a sparse polynomial. Okay, so in their case, they took f in the dense representation. Okay, so they took polynomials in n variables of degree d. They were given the entire polynomial, the all n to the d roughly coefficients. So the running time to begin with was at least n to the d because that was the input size. And then they had to answer whether it is a shift of a sparse polynomial. So whether they could compress that long representation to a much shorter representation. That was their motivation. And in fact, they asked even a more general question than this question. Namely, they wanted to ask to know whether f equals g of ax plus b. So they were not interested just in a shift to the variables, but also in rotating the space. So you rotate the space and you shift, and you want to exist a sparse polynomial that gives you this f. Okay? And they were able to solve this problem in the dense representation. So the input size is roughly n to the d, and they had running time which was something like n to the d square or some, it was perhaps quasi-polynomial in the dense representation. Okay? But they did not ask the question, they did not study the question of an implicit polynomial in the sense that it is given by some arithmetic circuit and not in the sum of monomials representation. Okay? So that was a sequence of work by, so they wrote several papers and some subsets of the author wrote different papers. I will not get into the exact details, but that was the lesson. They studied that question in slightly different settings, sometimes by quantum computer, sometimes by regular computer, and then they got this result. So these were some early work on that problem. And more recently, Niraj also studied the problem. So Niraj also studied that problem, whether f equals to g of ax plus b. Okay? And in Niraj's work, f was given by an arithmetic circuit. So it is like what we did. And in fact, this is a much more general question, right? You don't ask just about shift, but rather about whether such an a exists. So Niraj showed hardness result, basically that it is NP hard to answer this question. And the hard case was when A was not a full rank matrix. Right? I think that. So in general, this problem is NP hard, so hardness. So NP hard in the general case. However, Niraj was also able to give algorithms for very interesting cases of that problems. So also algorithms. So, for example, Niraj studied the case where G is, say, the permanent or determinant or some other interesting polynomials, and for the case where A is full rank. Okay? So here G is given to us in advance. It is one of a certain family of polynomials, like the permanent. A should be a full rank matrix. You don't know A in advance, but you are guaranteed that it should be a full rank. And then you want to find A and B or decide the problem. And in this case, Niraj was able to give an algorithm. So notice this is a more general problem than ours because of the A and B. On the other end, G is more restricted and A is more restricted. So we ask the question for general A and B. So this is a more general question in a slightly more restricted setting. What we ask is an easier question, but we allow more freedom to F and G. So that's, and if you will have time, I will also, we submitted the paper to a conference, and one of the reviews that we got showed us how to how to get an algorithm, well, similar to ours, but using ideas from Neeraj's work. So if I have time, I'll also explain this. There are some ideas in Neeraj's work that can solve the problem, not the, well, okay, there's some, okay, I'll try to talk about it at the end if there is time. So,
what the algorithm says, like, so you must have permanent determinant, you can express a polynomial in terms of permanent determinant. Is it like something to do with impact?
So it's a different question because the number of variables here and here is the same. Okay, so if you have a size S circuits, you need a permanent of size S by S, so the number of variables grow. So you cannot ask whether the polynomial G is a circuit of size S, because then A will not be full rank. Okay, and this is our problem, right? Deciding, I mean, it's a very good question. I mean, basically deciding whether a polynomial is a circuit of a given size is a very difficult question. And we know that the permanent is complete. So you can ask whether this tells you whether you can decide whether F is a size S circuit. But the point is no, because the number of variables here and here is the same. So you cannot take a projection of the permanent from more variables to fewer. That's hard. But, yeah. Okay. And there are many problems that really reduce to this. I mean, you can reduce tensor rank to this problem. I'll not get into it. I mean, you should ask Neeraj to talk about it. But that's basically, okay. So this is more or less the background. And yeah, now I would like to explain the idea of the proof of the theorem.
What is the problem here? What is the problem statement? You're supposed to find A, is it? Find A.
You don't decide whether such A and B exists. But I think that you actually find A and B. I mean, it gives you a way to find A and B. And it's randomized algorithm. Okay? It's efficient randomized algorithm for the, it's a very surprising result when you see it. It's like, it cannot be true, but apparently it's true. Okay, so it's a very nice result. So I'll now show the proof of this algorithm, and I will use, just let me say a motto that Amir and I saw on the wake today that will explain what I also do. And we saw a sign that says, wisdom is to know what to overlook. Okay, so I will try to hide as many details as possible. I will just give the high-level ideas. And I think that if you follow what I say, you will see that I'm not proving this theorem. But you can try and catch me. It can be like a game. I'll cheat and you'll try to find it, to catch it. And if you have time at the end, I will explain, or I will keep the right to remain silent. Okay, so let's go, let's discuss the proof, okay? And again, I'll not be, I think it will be hard to see from what I say why it is enough to have only those closure properties, but if we have time and you push me, I can say a few words about this, but it's a bit delicate. Okay, so let's look at the proof. So, okay, so we have two polynomials, f and g, and we have to decide whether there exists a sheaf such that f of x equals g of x plus b. Just have to see which comes from which class. F is g is in M2 and M2 is closed under sheaf. Good. Okay. Right. So we have to decide whether this is the case. Okay. So let's try to see what this means. Okay. What does it mean for f to be equals to g? So it will be convenient to speak about the homogeneous components of f and g. So let's denote by hk of f the homogeneous component of degree d, of degree k, sorry. Okay, of f. So in other words, maybe I should continue here. So in other words, f, you can write it as just summation of age k of f. Okay. That's the same with both polynomials of degree d. Okay. And similarly, g is summation of hk of g. Okay. So these are the degree k part of f. I'll just go over all degree k. And this is the degree k of g. Great. Okay. So let's see. So what is g of x? What is the highest degree component of g of x plus b? So what is this component? If you think about it, when you shift a monomial, you only affect lower degree terms. You don't affect the maximal degree terms. So this is hd of g. Okay? So if you want this to be equal to hd of f, then it must be the case that hd of g equals hd of f. Okay? So as a sanity check, first we would like to check whether hd of f equals hd of g. Okay, that's one question we have to answer to ourselves. But this is clearly something you can solve with PAT. Okay? Yeah, I don't know if you noticed or not, but I already cheated. You can think about it, but yeah. Anyway, what I said is true, but there is a cheat hiding behind the truth. Okay, so that's degree D. Now, okay, now let's go to degree D minus 1. What happens there? So what is the degree? So what is the degree h d minus 1 part of g of x plus d? Now, if you think about it, so who can contribute to this part? Certainly, you can get gd minus you can get hd minus 1 of g, right? Because this part doesn't change. It still is the same. It's a degree d minus 1 polynomial, and when you shift, it only affects lower degree terms. But you also get a contribution from hd of g. And what is this contribution? If you think about it, and not with just something, as Michael says, you're doing the privacy of your own mind, you just realize that this is summation of bi and the derivative of h d of g to the xi. Okay? When you shift a monomial, the best way to see it is to always think about monomial, because all those equations are linear. So think about a single monomial. What happens when you shift it? It's even enough to think about x to the k. When you shift it, you get x plus a to the k. What is the degree k minus 1 part? Right? Just open the binomial and you get this thing. Okay? So this is really. Okay, great. So now what do we have to study? Now we have to decide whether hd, I think I switched f and g. Yeah. Okay. Yeah, I want, okay, never mind, because I'm cheating anyway. Okay, so, so basically what you, okay, but let me still write it, I'll write it here, okay? We have to decide whether this equals hd minus 1 of f plus, it's b, just take instead of plus b, do minus b, it doesn't matter, okay, plus summation. This is not right, this is actually okay. I make it out to tell the truth and lie, so it's like a good politician. bi the hd of f to the xi. Let's just say that, Okay, don't worry about this, okay? Let's forget about it. No, really, I just, f of x minus plus b equals g of x, okay? Instead of, Okay, sorry. Yeah, because I want the class N1 to be closed about first order derivative. That's why I want to take f here. That's it. So, anyway. Okay, so we have to decide this. Okay, look at it. Now it seems more difficult than that question. But what do we have here? Right? Remember, we are looking for those bi's, right? These are the coefficients of the shift. This is the component of the shift factor. This is what we are looking for. And if you stare at this equation, you realize that you have a linear equation in the bi's. What is, right? So what are the coefficients? The coefficients are arithmetic circuits. Never mind. but it is linear equations in the BI, linear equation in the BI. And you can think about it as a system of linear equations. Why? Because for every value of x that you plug into g and f, and the partial derivatives you get, right? You can pick some x, plug it into the thing, you get a linear equation in the B. Pick another x, you get another linear equation. So this actually gives you an infinitely many, or depends on the field size, infinitely many equations in the BI. So you can solve it. Right? You solve a linear equation, you get the BI. Right, if this was a full rank, and what do I mean by full rank? Let's say that by going over all substitutions, we would get a system of full rank in the BI, then there would be a single solution BI. We'll take that BI, and then we'll just have to check whether indeed when you shift G, we get F. Right? If this was the unique solution, then find it, let's say that, okay, I didn't explain now, but let's say that we can solve such systems of linear equations. Okay, assume we can solve this system. And assume there is, right? So if we can solve such systems, and if there's a unique solution, then we are basically done, right? Because we solve this system, we find the unique solution, and then with a single PIT call, we can check whether, I don't know, f of x plus b, or let's be f of x equals g of x minus b, right? Instead of shifting f by b, I shift g by minus b, okay? So if this was the case, then that's it, right? That would be the algorithm. So what is the only problem here? So this we can do. This is something I have to get to. Actually, I'm talking so I can get to it. I can explain it. This is not necessarily true. Okay, there might be many. Or look here, I only consider the d-1 component. Right? Maybe the d-1 component has many shifts, but if you consider more components, you get fewer shifts. So this is the part that doesn't work. But if there was a unique solution, I could just get it and run a PIT and I would be done. Okay, so let's say that we started the algorithm, we got this set of equations using our knowledge how to solve such systems, which I didn't explain, but it's not very complicated. We can do, we solve it, and we get a space of solutions. What now? It's a vector space. We cannot run over all vectors in the space. There are too many of them, right? Especially if the field is infinite, right? Okay, so what do we have to do next? We have to go to d-2. So let's do it. So what will be the third thing we do? So now let's look at, let me do it now accurately. What is hd-2 of f of x plus b? Right? I had to do it also with f, etc. So now, okay, let's again, what I get? I get hd-2 of f. Plus, I get an equation, bi, d. Now it will be the hd-1 part. However, now I will also get contribution for the degree d part. And now it will be a second derivative. So we'll have things like summation bi bj, we'll have dxi dxj, and d square of h d of f. And again, I will have to ask whether this equals hd-2 of g. And now, I don't know if you look, but when I first look at this thing, I got worried. Why? Because it's no longer linear. It has quadratic terms. And if you have imagination, you can imagine what will happen in the next. You get cubic, then they give 4 things, and they give 5 things. And how do you solve such systems? Right? So this is the first problem we face when thinking about this problem. However, there is some very simple observation that once you make it, makes everything, all the problems disappear. Okay, so let me set it here. Oh, I'm out of board. So let's look at so this is our problem. I will now explain how to deal with this case, and I think that if I show you why this is not a problem, you'll also understand what we'll do in the next steps, etc. So I want to go back to this step and think about it, okay? So what do we do? We want to solve equations of the following form. This is what we want to solve. And we said that if we have a unique solution, then we are fine. But what does it mean that there is no, what happens when we have more than one solution? So it means that we find two different solutions, right? We find another HD minus F. So let's say that B is the true shift. Okay, if there is no shift and everything we do won't help, and at the end we'll run some PIT algorithm and we'll be okay. So let's assume there is shift. So let B be the true shift. And let's take any solution that we find, just pick some solution, okay? So we find some solution, let's say summation AI, df to dxi. So both the true shift is a solution and some solution is a solution. Now what happens if you subtract these two equations from each other? It's a solution to the homogeneous system, right, in a linear system. So basically what you get is you get the summation of bi minus ai df to dxi equals the opposite. It's not df, right? It's h df. Okay. Now look at this equation. What does it mean? It means that there is a direction. I mean, this is like a directional derivative, right? When you have a multivariate polynomial, you can take a derivative according to each one of the coordinates, but you can also take derivatives according to lines. This means that when you take a derivative according to that line, you get a zero derivative. In other words, the polynomial does not change along that line. Now, let's try to understand what it means. Let's say that this difference was just x1, namely, it was the, yeah. So let's say that the vector, for simplicity, let's say that this vector was just the vector 1 and all zeros. Okay? Then what would this equation be? Just be dHd to dx1 equals 0. What does this equation tell you? It tells you that hd of f does not depend on x1. Right? Take a derivative according to x1, you get 0. But this also means that if you take a second derivative according to x1, you also get 0. And the third derivative, you also get 0, etc., etc., etc. So if you think about it, this means that in this direction, nothing changes. So also the polynomial does not depend, right? So if a polynomial does not depend on x1, then, right, so then f of a will be equal to f of a plus e1, right? Because changing the first coordinate will not affect the polynomial. If you think about it a little more, then you realize that this implies, this fact implies that summation bi bj, which is the true shift, okay? D square hd of f equals this is just equal. And what's the reason? The reason is that if the derivative according, let's say that this was x1, if the first derivative is 0, then it doesn't take more derivatives, you still get 0. If you take two derivatives and you do some manipulations, you get to this equality. Okay? So what does it mean? Just think about it. B is the true thing, the one it's a shift we are looking for. Okay? And A is any solution that you found. So now let's go back to this equation. Remember, we have to solve this for B. And we would like to reduce it to a linear system, not a quadratic system in B. So what can we do? We can take any solution that we found in the previous step, really no matter, just any solution, and just plug in AI. And then solve the new linear system in B. What will you get? You get, again, a space of solutions. Now what you'll do? You go to the next level, to D minus 3. you will set up the equation again. You get the cubic terms. And now, instead of working with cubic terms in the B, you plug in the solution that you found. And again, solve the linearity. So let's try to summarize this. This was just for the case that equivalence A is all one vector. It is 1 and zeros. That, okay. Yes. And this means basically that if you take, basically what I want to say is that okay, we know that the derivative in direction A minus B is 0. Okay? So what is df to dA? This is exactly like df to dB plus A minus B. Because I've done nothing. And the point is that changing even the derivative in that direction doesn't do anything. So you can, okay, now let's take two derivatives. What is B squared according to D A squared? I'll just do this twice and get rid of D minus A in each time, right? This will be D A times D plus A minus B of HD of F, right? I've done nothing, right? You just, now if you look at this, then you can just erase it. There's no effect. Now you switch the, you do the same thing again. And that's what we need basically. So that's what's going on. Okay, so that's just yeah. A and B are different by only a direction. There's no influence. Actually, this is not a check. Okay, but okay, so how does the algorithm look like? The algorithm looks like this. It will be done in stages. And let's say that in the kth stage, we set up the following systems of equation. So let's say that okay. So in the first stage, we want to solve a to the minus 1 of g. We solve this. And we found some solution. Let's call the solution A1. Like the solution to the first. And in the second step, we find solution A2, etc. So what happens in the kth step? What we are going to do, we're going to solve the following thing. So this should be, I guess, HD minus K of G. Plus, what's happened now is that you take the degree d minus k part of, I guess, this solution. Like you just take all the things you already solved for and Okay, so what is this part? This amounts to, well, for the quadratic part in the second stage, and for the quadratic plus cubic part in the third step, etc. So you take the solution that you already found. I mean, basically, if you think about it, this part about derivatives, right? What is this part? It's just like taking the homogeneous component of the grid D, shift it by B, get a new polynomial, and then take its component of the grid D. So that's why this. Basically, this should be a term involving the Greek K polynomials in the B's. However, we don't need to use the B. You can take any solution that you found so far and plug it in, okay, to get a system of linear equations in the BIs. So what do we do in the kth step? In the kth step, we set up all those equations and we solve them. And we get a solution. Now we set up the K+1 step. And then we solve again all systems, etc., etc., etc. And so at each state, we find a solution that satisfies everything. We plug it in to get a new system of equations and we solve it. What do we do at the end? At the end, the last step, let's call it, I don't know, the D step, the D+1 step, check whether f of x equals g of x minus the solution that you found so far, I guess this. Okay, you find some solution, then you check. Okay. And that's it, basically. That's the algorithm. And so, yeah, so what happened here? I didn't show you any PAT thing, right? Except for the last step. So the PAT is hidden here because I didn't explain to you how to solve systems of equations. So we need PAT for this. But let me do it in a second. So again, so what happens here? We set up a system of linear equations and we solve it. That's how we proceed. And now why do I have to, so if you think about it, the last step is redundant in some sense, because if we found something that satisfies all the previous themes, then it is a shift. Because we check that the D part agree and the D-1 part agree, etc. So the last step seems redundant. Right? So why do we do it? So the reason that we do it is because of the part that I didn't show you. Right? The algorithm can have, okay, let's, I mean, okay. We do it because in some cases, we will not really solve the system of equations, but rather we will get a candidate solution, such that if there is a solution, this will be the solution. But we will not be able to verify whether this solution works or not. And the reason that we will not be able to verify it is because we assume very little about the circuit classes that we have. We do not want to assume that we have a PAT algorithm for a complex class. So what we will do, we will put our trust in the algorithm. We just find a candidate solution, such that if there is a solution, this will be the solution. And this will then propagate throughout the algorithm. And in the last step, we will be able to use PAT for this. This is the PAT that we assume. Okay. So now I am really running out of time. I want to explain how to solve systems of linear equations. But by the way, by now you should have, okay, let's see. So, yeah, so let's go here, right? How do we solve a system of linear equations? Okay, think that if I explain to you how to solve this system of linear equations, or basically any system involving arithmetic circuits, then you'll be able to understand really all the details of the algorithm. Okay, so what is the idea? So let's assume that we have, I'll just write something more general, F1, Fn, and G, which are all arithmetic circuits. And we want to decide whether there exists some linear combination AIFI, which gives you G. Right? This is basically solving linear equation, right? I mean, this is what we ask you, right? We have the BIs. The BIs are those things. We have the coefficients which are given to us. These are the fi is the derivative according to xi, and g is the constant term, right? It will be this hd minus 2 and this hd, right? Yes.
The two ways of thinking. I mean, these fi's
potentials we thought of as polynomials.
Yes.
So that is one thing. Or we just open up the polynomials and write down the system of equation for each equation.
Exactly. So yeah. So I think about the Fi is given by arithmetic circuit, so it's an implicit representation. But what Jacob said, just assume that we had the polynomials written to us as a system, or as a list of coefficients. So let's assume that you get, like, let's say that you have this matrix. You write down F1, you write down Fn, and you write down G. What do you mean by write down? You just write it as a list of coefficients. Right? Here there will be some monomial, x to the d, and you will put the coefficient in F1, F2, to Fn. And then there is such an A, if and only if you can find an A that makes this times this. So we're just solving a system of linear equations. So exactly, that's what we would like to do, but the problem is that those are n-varied polynomials, and those matrices could be huge. That's the only problem. So let me show you how to solve it with a black box identity testing algorithm. Okay, so what we'll do something even more general. What we'll do is we'll take F1 up to Fn and find linearly independent polynomials among them. We'll just find the bases to F1 to Fn. Okay? So let's assume we have a black box PAT, or basically a eating set. Okay? So eating set for what? Let's assume for everything. That's for polynomials of that form. So linear combinations of the Fi minus G. Okay? So for, I don't know, summation of alpha I, Fi minus G. Right? Let's assume that we have eating set for polynomials of that form. Okay, then what we will do, we'll do exactly what Jacob recommended, but instead of writing it as a list of coefficients, we're going to write its list of values on the heating set. So we're going to set this matrix. Here we will have the point of the heating sets, and we will have F1 up to Fn. And for any point, I don't know, give me a name of point, V, we'll write here Fi of V. Okay? Right. This is V, there will be Fi of V. Okay? So we're going to fill this matrix with the values of F1 on the heating set, F2, etc. And here we'll have the same thing with G of V. Okay, we're going to set these two matrices, and then we're going to look for a solution. And I claim that if we can find such a solution, then this holds. Now look, we didn't coefficients. We just looked at a small set of values. And what's the reason? Because what will this A satisfy? It will satisfy that summation of AI Fi minus G evaluated at V is 0 for every V in the heating set. But what is the meaning of a heating set? A heating set is a set of points such that if the polynomial is non-zero, then it gives you non-zero on one of the points on the set. So if all of these are 0, then that polynomial must be 0. So we've solved linear. So in the black box setting, in the black box setting, this task is very easy. In the white box setting, it is more delicate because you do not have such a set of points. So what we do is we gradually find a set of points, V. If you know think about the SAT problem. The SAT problem is a question of deciding whether something is satisfiable or not. Like PAT, whether something is 0 or not. In the SAT, if you know how to answer the decision problem, you can also find the satisfying assignment. Why? Because you get a SAT formula, and you plug into x1 the value 0. And you ask, is it satisfiable or not? If not, then you made a mistake and you plug in 1. So the same here, you will be able to construct a set of points that will give you a full rank matrix, and then we'll solve this equation. So this is really hand-waving about the white box case. So good, so these are basically all the details of the algorithm for the case of general circuits. Now I said that it cheated, and it cheated a lot. Now what is the cheat? And so I'm going to still just 5 minutes to explain the cheat, but I don't have much time to go into details of what's going on. So remember, I wrote some closure conditions about M1 and M2. So what were those conditions? Yeah, I think I erased them. But basically, N2, all we required of N2 was to be closed under shifts, not even under homogeneous components. Now look, what do I do here, right? I have to run PAT for summation of Fi minus G. What are these things? If you think about it, they involve the homogeneous components of both polynomials. So HD minus 2 of G is not even something in my class. I do not have the assumption that I have PAT for such things. Right? So nothing can work, right? So the point is that when did we need the PAT for this linear combination? Right? Well, think about the black box case. Okay. So basically, we just needed to, we set up, we found a set of points that for the FIs, really, if you have a Eating set for the class M1, it will give you a set of points such that this will be full rank, or the rank of this matrix will be the rank of the FIs. Like it will tell you which one of them are linearly independent. Now you will not be able to verify whether this A is indeed a solution or not. But the point is that if there is any solution to this equation, it should be A. So what you do is basically, let's assume that we have a Eating set only for linear combinations of the FIs. And this is something weird because the linear combination is just a directional derivative of F. And this is something we assume weird. So if you think about it, when you write this matrix, you can find the linearly independent columns inside it. So you just restrict yourself to the linearly independent columns. And now if there is a solution, it must be unique because the columns will be linearly independent. So basically what you do is find a candidate A. And you know that if there is some solution, it must be that solution. And you just don't verify it. You just continue with it. Continue and continue and continue. And now if there is a solution, then you found it. But if there is no solution, then okay, so you catch it in the last step. And that's why you need this PAT. So there are some more cheats hiding inside, but this is basically what's going on. We assume we require very little of our circuit classes, so we have to do everything very carefully and make sure that we do not ask PAT questions for things we cannot compute. And yeah, perhaps I can just take 5 more minutes to explain a different approach to this algorithm. Is it doable? Okay. So as I said, we submitted this paper to a conference and got one of the reviews suggested a different algorithm. And this algorithm is in some sense, it's the same as ours, just stated in a different language. But it looks in some sense nicer. So let me explain what's going on. What is the other approach? So let's look at the first equation. Yeah, by the way, I cannot give credit because I don't know who the referee was. So, yeah, so, but some anonymous referee gets credit. So we have that equation. And we say that if there is a unique B, then no problem. You take this unique B and you check and you're done. But what happens if there are many B's? We said then we run into problems and then we look at D minus 2, etc. But what the referee said the following nice thing. Look, remember I explained to you that if there are several solutions, then the difference between the solution gives you a direction in which HD is fixed, right? It does not depend on that direction. So basically what you can do is you can find the set of all solutions to this equation. And you basically can reduce the number of variables because you can just eliminate in HD all the directions in which you do not depend. For example, if B minus A was E1, you can just erase X1 from HD of F. So basically what you do is you first solve the system of equations. You find the space of solutions. Then you reduce the number of variables to only the essential variables. You remove all the directions in which you do not, your derivative is 0. And then you get a polynomial of full rank. Basically, it depends on all its variables. And then you solve it again, and then now the shift is unique. So you reduce the number of variables of HD of F to only the essential variables, and you find the unique shift on them. And now that shift is fixed on those variables. You cannot touch them anymore. So now you go to D minus 1, and you solve the thing there. You again reduce to the essential variables, fix the shift. So you basically build a shift step by step. Now, so this is basically what happens here, because we find a set of solutions and then we prune it, right, to find it smaller. So it's like, instead of building the shift step by step, we take the dual approach in some sense. Now, what is the so this can be seen as just two different ways of describing the same process. However, there is some inherent difference between this approach and what I presented. And what's the point? The point is that, what do we say? We say we find the irrelevant directions, and then we basically we do some linear transformation to get rid of irrelevant variables. But once we do this linear transformation, we need to solve linear equations not for our original polynomial f, but rather for an f composed with a linear transformation. Okay, maybe what I'm saying now is too vague. But basically, what happens in this process is that you have a linear transformation that you have to compose into a polynomial to get rid of irrelevant variables. And now you need PAT for classes that are closed under linear transformations. And all the classes that, that's a problem actually. Because you need a class that's closed under linear transformation, homogeneous components, partial derivatives. So, of course, the class of general circuit satisfies it. So this gives a new randomized algorithm for the general case. Or if you want to work with existing PAT algorithms, then you better work with our proof because it requires less of the circuit classes.
Are there any PAT classes that are closed under all of these things and linear transformation?
So no. So I mean, for which we are deterministic PAT, no. Well, yes and no, but if you work out the details, so for example, one class that I mentioned that we can get a deterministic PAT is the class of sigma pi, sigma k versus sparse. Another class you can get PAT is read-once arithmetic branching programs versus read-once arithmetic branching program. So if I give you two read-once ABPs in the same variable order, then you can decide whether one is the shift of another using this algorithm. Now the class of read-once ABPs or even set multilinear ABP is not closed under linear transformations. However, you can prove that if you get any linear transformation, for this class, it works layer by layer, so your still should be okay. But that requires another proof. So I guess that, so it's not going to be closure under general linear transformation, but under a specific form of. So set multilinear ABPs, it should work, but basically that's so the proof that I really only end-waved about reducing the number of variables. I didn't write it, but I think that after you've seen it, I find it a bit simpler than ours because you don't need the extra observation that the summation BI-BJ equals summation AI-AJ. On the other hand, it seems that you need a stronger PAT assumption. And that's why I still stick with our proof. Okay, thank you.
Please wait near West Canteen. We'll meet again at 5:20.